reservations in two-way slabs by means of yield lines. This video will deal with the cases 31 to 35, and it's about two-way slab with fixed end supports on the shortest side and two simply supported on the longest side. We will handle now case 31 about an edge A square hole. It's in fact edge A because we have the smaller side is A, and we also have edge B hole, we call it like that, when it's on the longer side. So case 31 is an edge A square hole. We'll first look at the maximum bending moment of a slab, case 31 to 35, without a reservation in it. When we have a reservation, like it's shown here, with B over A bigger than square root of 3, then you will have a yield pattern in this formation. If the ratio B over A is smaller than square root of 3, then you will have a yield pattern like it is indicated here. So those cases 31 to 35 are a little bit special because they are split into two different cases. On the limit between the two different cases, we have, of course, this type of yield lines. So we call this horizontal because of this horizontal yield line, and it means when alpha is bigger than the square root of 3, then you have the horizontal yield line pattern. When it's alpha equal to square root of 3, we have this kind of yield line pattern, and we call vertical because of the vertical yield line pattern when alpha is smaller than the square root of 3. Let's start with the horizontal case where the yield line is horizontal. The yield line in the corner where two rotation axes cross, we use the 60-30 degree rule. So this is 60 degree on the side of the fixation and 30 degrees where it's simply supported. We do it in the opposite corner too. And now we do it on the other side, and then we make the connection between the two intersections. Of course, we have also the negative yield line where the slab is clamped, is fixed. And that's the yield line pattern that we consider. Geometric characteristics, this is S1. And S1, you can calculate it with the cotangus rule of a triangle. It means that S1 equal to A square root over 2. S3 is of course the same, A square root over 2. S2 is half of A, and S4 is also half of A. So we have the geometric characteristics in the horizontal case, and we see that the yield lines in the positive bending moments, we call it M. For the negative bending moments, we call it M1. In principle, M and M1 can differ from each other with a certain fraction. But in most cases, the reinforcement on top and bottom of the slab equal. So for our case, we will suppose that M is equal to M1 and is equal to M2. The work done by the external forces can then be calculated. It is the summation of the triangle areas, and it's equal to S1 times A, and on the other side S3 times A, and the mean deflection is delta over 3 because of the triangle. What's left is the rectangle. It's A times B minus S1 minus S3, that's this little piece, times the mean deflection is delta over 2. Then we can substitute the values of S1 to S3 in it, and then we have this expression. The work done by the internal forces is the bending of the yield line M projected to this axis. So it's M times B times the angle of rotation, which is delta over S4. Here on this side, you also have M times B divided by S2. And on the shortest side, we got A times M divided by S3. There again, we got A times M divided by S3. And on the left-hand side, we got M times A divided by S1. And for this, it's also the same. That's where the 2 is coming from. We can substitute the different variables. And by stating D is equal to E, we got the bending moment M, which we call M0 because that's the maximum bending moment without the reservation in the slab, and it has this expression. Now we can do the same for where the alpha is smaller than square root of 3 for the vertical configuration of the yield lines. Again, the 60-30 rule for the different corners. And then we make the connection between the two intersections. The negative bending moment is then also indicated. The geometric characteristics, S1 is now B over 2, S3 is also B over 2, and then S2 is again the cotangles rule, which is B divided by the summation of the cotangles of the two angles, which is B square root over 6. And S4 is the same, is also B square root over 6. Now we can calculate the work done by the external internal forces, but first we will use again the positive bending moments of the yield line. It's M, the negative is M1, but because of the symmetry of the reinforcement, M is equal to M1. The work done by the external forces is the summation of the triangles, which is now on the top here, B times S4 plus S2 times B times the mean deflection is delta over 3. And for the other, for the rectangular section, we got the length B times its little piece, which is A minus S4 minus S2, and this multiplied by the mean deflection delta over 2. Substituting the variables give you this expression. The work done by the internal forces are the bending moment M projected on this axis of rotation, which means B times M divided by S4, because delta over S4 is the angle of rotation. On the bottom, we got M times B divided by S2. And on the side, we got M times A divided by S3. We got that 2 times. And on the other side, it's M times A divided by S1, and we got it also 2 times. Substituting gives you this expression, and when E is equal to D, we find M, which is then equal to M0, which is the maximum bending moment without a hole in the slab. Now let's just check the formulas. For a square slab, A is equal to B. It means that alpha is 1. So we are in the situation of the vertical yield lines because alpha is smaller than square root of 3. Then we can use this formula that we've found in the previous slides. And you put A equal to B, and we find Q8 squared over 37, which corresponds well with the value cited in the literature. Now consider an existing slab where the reinforcement before and after the reservation made in the slab is equal. We know that the bending moment of the slab with the reservation is proportional to the ultimate limit load times a factor which is only depending on the geometry of the slab and the reservation. For the slab without the reservation, we have a similar um, expression. And then we can see easily that Q over Q0 and C0 over C and M0 over M are equal. For the further calculations, we will use, instead of E, because it's always dividing by delta over Q, dx instead of D, because it's dx is D over delta M. And when E is equal to D, it means that the bending moment is equal to the load in ultimate limit state times EX divided by D. And we define bearing capacity as 100 times M0 divided by M, or because it's the same, that is 100 times Q time divided by Q0. We look at now at case 31 with the reservation. We will now look at case 31, HA square hole. And we start with the horizontal yield pattern. It means alpha is bigger than square root of 3. First condition must be a two-way slab, so B must be between A and 2A. It's a square reservation, D1 is equal to D2. It's a reservation at the edge, so it means that D4 here is 0. And this reservation is between the two yield lines mentioned here. So that are the boundaries of this reservation. We put in here the values of S1 to S4. And of course, D1 must be smaller than A over 2. And to visualize the reservations, we see here the reservation in the middle, and it goes from the left limit, which is this one, left limit, to the right limit, which is this one. These are the other values of S, and this is when we calculate to 3 decimal points, then you have this expression. Now we can calculate the work done by the external forces. It is, of course, the formation of the triangles, which is A times S1 plus A times S3, and the mean deflection is delta over 3. And then the rectangular sections, we got B minus S1 minus S3 times A, but the reservation, we must subtract it from it, and this is D1 times D1, and the mean deflection, or let's put it, the maximum deflection there, it's not delta, but it's D1 over S1 delta. So this is S1, and this is D1. And the mean deflection of this system is delta over 2. So we can substitute the different variables and this expression. The work done by the internal forces is then equal to this bending moment projected to this axis of rotation. So it's M times B. Angle of rotation is delta over S4. Then we got the yield line at the bottom. It's M times B, and the deflection is delta over S2. But S2 is equal to S4, so you got 2 times B over S2. And then we have the yield line A times M over S3, and we got this 2 times. And on the other side, we got A times A over S1. So we got that 3 times. It's there once, and then we got 2 times this. And then for the reservation, this is the reservation is cut. The yield line is cut by the reservation. then we got A minus B1, and the angle of rotation is delta over S1. We substitute the values of S, then E is equal to D, and we get M from it. But at the same time, we will use dimensionless parameters. And then you have an expression of the maximum bending moment in case of the horizontal situation, which is equal to this formulation. We notice directly that this formulation is independent of T3. So we must be very careful now because the value, the conditions on D3 must be correct, otherwise this formulation is not okay. Now we look at the vertical pattern of yield lines with when alpha is smaller than square root of 3. We again have the condition of the two-way slab, the square reservation, the edge, because the reservation at the edge D4 is 0, and between the yield lines, of course, of those two values. You can now visualize it with vertical yield pattern, and then you got the left-hand side to the right-hand side and the values of S. And this is then the limit of B3 from left to right. We can calculate now the work done by the external forces, which is the summation of the triangles. So it means it's B times S4 plus B times S3, oh, S2, sorry. So, and times the mean deflection is delta over 3. And then for the green area, we got B times A minus S2 minus S4. And, and now we have something too much, so we have to subtract the reservation, which is D1 times D1. And the deflection there, the maximum deflection is delta times D1 over S1. And then the mean deflection of that whole system is D over 2. You can substitute the variables and arrive at this expression. The work done by the internal forces, this bending moment M is projected through this axis, so it is M times B, and the angle of rotation is delta over 4. Here we got B or M times B divided by S2. On the other side, we got A times M divided by S3, and A times M divided by S3. And here we got A times M divided by S1. And this is A minus D1 divided by S1. It gives you this. We fill in the values of S1, 2, and 3, and we got this expression. D is equal to E, so we can find M, and at the same time we work with dimensionless parameters. So the maximum bending moment for the vertical system is then equal to this expression. Then this formulation is independent of D3. Let's give an example of a slab of 250 millimeters with a concrete cover of 40 millimeters, floor finish of 2, and a mobile load of 10. And the dimensions are given in this drawing. What is now the needed reinforcement for this situation? We first calculate the load in ultimate limit state, which is the permanent load times 1.35 plus the mobile load times 1.5, and it gives you 26.14 kilonewton per square meter. The different variables, A, B, and D, from the input of the example. Alpha B over A is then 1.375, and alpha 1, D1 over alpha is 0.25. The square root of 3 is 1.7, so this is smaller than the square root of 3. So the maximum bending moment is then equal to this formula and gives you 66.77 kilonewton meter per meter. Then we calculate the lever arm to convert this into reinforcement. And the mean lever arm is 198 millimeters. And the needed reinforcement is then 1.1 times the maximum bending moment divided by the lever arm and the yield strength of the reinforcement. Gives you 950 square millimeters per meter, or diameter 12 every 120 millimeters. You can also choose for a bigger diameter because this is a step up to 50, so you can easily go to a spacing of 200. So diameter 16 every 200 seems to be better. Of course, when you use 16, you adapt this rebar size to calculate the correct lever arm, and you recalculate the needed reinforcement. Second example, you have an existing slab reinforced in 2 directions, and we want to make a reservation into the slab, a reservation with size of 2.4 by 2.4. And the question is, can we do that, making a reservation like that? We know that the bottom and top reinforcement of this slab is equal, but we do not know the original load where it was calculated for, nor the exact value of the reinforcement. So we know that the parameter alpha is 2, b over a is 2, and alpha 1 is d1 over a is 0.4. Now we can calculate m0 over q, which is the maximum bending moment without the hole, and we divide by q because we don't know the ultimate limit load. This is only depending on geometric characteristics, and we find that this is 2.029. We calculate the maximum bending moment with the hole, and we calculate m over q, and it's equal to 1.997. So this means that the bearing capacity, or 100 times m0 over m, is 102. It means that the reservation, which is quite large, in fact, but it has no loss in bearing capacity. So bearing capacity, we define it as 100 times the maximum bending moment without the hole divided by the maximum bending moment with the hole. We use dimensionless units. So the bearing capacity in case 31 is a function of alpha and alpha 1. The restrictions on the case 31 are, of course, two-way slab, so alpha being 1 and 2, alpha 1 begins between 0 and 0.5, and alpha 3 between those two limits. And now you can calculate with this formula, you have, for instance, for bearing capacity for the vertical situation, you have 100 times m0 vertical divided by m alpha 1. And this gives you this expression. And bending the bearing capacity for the horizontal situation, it's m0 horizontal divided by m. You got this expression. And then we know that the bearing capacity of the slab is equal to this equation. Now we can put it into a graph. X-axis is the size of the reservation, y-axis is the bearing capacity, and we do it from alpha going from 1 to 2. These are the green curves. These are the possibilities. We know that the condition was alpha 1 must be smaller than 0.5, and alpha 3 must be limited between those two values. Now, alpha 2, to obey this rule, then alpha 1 must always be smaller than 0.4648 or 0.464 alpha. That is when this equal to that. Otherwise, alpha 3 cannot be expressed. It's not right. Now you see that there are two conditions of alpha 1 depending on alpha. So on the limit for alpha bigger than 0.5, 0.5 divided by 0.464, which is 1.08. So for alpha bigger than 1.08, this condition is the most important one. And for alpha smaller than 1.08, this condition is the most strict one. So it means that this graph is made for alpha up till 1.5. No, it's 1.46 made. In fact, it can go to 1.5 or to 0.5 for alpha smaller than 108. So in the limits of alpha 3, we see that the left border corresponding with this and the right border is corresponding with this. We can see that for alpha 1, the bearing capacity is untouched for a value of alpha 1.233, alpha equals to 1.5. It's the bearing capacity is untouched for alpha 1 bigger than 0.295, and this is for an alpha 1 bigger than 0.336. We take the previous graph and look at this left-hand side of the graph, and we see that this is the area that we should take care of, because then the bearing capacity will be lower than the original one when we make the reservation of type 31. But when you look closely, you see that the maximum loss is only 1%. So that is not significant at all. And we can say that the bearing capacity is untouched by making a case 31 reservation. To be absolutely sure, we can say that there is no bearing loss when the reservation is larger than 1/3, 0.33, somewhere here, when it's larger than 1/3 of the smallest size of the slab. So as a conclusion, square hole at the edge of a rectangular concrete slab type 31 and no significant loss of bearing capacity as long as the yield lines are not crossed. So this is for the vertical situation and this is for the horizontal situation.